Good afternoon, good morning, good evening, all these things. This is Professor Bim Swester from Kathmandu University, and we have colleagues from Professor Panmanas Sirisimbur from Thailand. I work at Kathmandu University, and Professor Panmanas is King Mongkut Institute of Technology, Landraba. And today's topic, we are going to discuss about NIR of biomass characterizations. In our team, we are working between Kathmandu University and King Mongkut Institute of Technology. Uh, our goal is to develop affordable economic biomass NIR sensors for developing countries. We are a team working together from Nepal, myself and Prakash Manandar, who is currently in MIT Boston. And from Thailand, we have Professor Panamanas Sri Sambun, Professor Wanchut Sachu, Dr. Trapi Nakawajan, Dr. Jayut Hongchuan from Ag Engineering Department, and Professor Chuyong Pongtamik from Telecom Engineering Department at King Mongkut Institute of Technology. Similarly, we have Dr. Jesada Posum from Konkan University and Polpat Nakon from Spectral Technology Instrument Company in Thailand. And from Germany, we have Dr. Axel Fonke at the Karlsruhe Institute of Technology. And from Philippines, we have Mr. Joy Maria Maja at Clemson University in USA. The actually, though our goal is to develop fast and economic and reliable sensor technology, we would like to share with you some of the activities that we have worked on NIR spectrometer for biomass character. As you can see here, we need to have collect the biomass, and these biomass need to be converted into small chips and powders that could be measured for their spectral characteristics. And with these spectral characteristics, we try to identify the entire properties or other characteristics as well. Let me talk briefly about biomass of Nepal. Here you can see in our biomass, we have basically collected fast-growing trees that are Alnus nepalensis. You can see here, this is Alnus nepalensis. These are Eucalyptus camapudinus, and this is a Pinus roseburgi, Bombax seba, and Bombusa vulgaris. Similarly, the agricultural residues here, you can see the rice chaff, that is Oreja sativa, Sacum officinarum, that is a sugarcane bagasse, Giamas, that is a comb, that is a GMAS, that's a husk cell, and a GMAS, that is stowers. As we are presenting from Nepal, Nepal is a central part in South Asia, and we have collected a sample in one of the district in a mountainous region, that is a Kabre, and in the southern part in Sorlai, that is a plain area of Nepal. And from Kabre districts, we have collected. Kabre lies in the mid-hills of Nepal, and we have collected this Alnus, Pinus, Bombasa, Giames, Shielcom, and Stowers from Kabre. As we have collected the agricultural residue and others from the Salai district, that is Eucalyptus, Bombax, sugarcane, and Saccharum officinum from Salai district in the southern part of Nepal. And these samples are collected, weighed, and stored in a small sachets. And these sachets are sent to the laboratory and where the spectral characteristics are measured. As you can see, these are the different samples that are collected and converted into small pieces and put in a sachets. And samples are sent to the laboratory. Their spectral characteristics, before finding their spectral characteristics, the samples were crushed into powder and they are kept in instrumentations for NIR spectral analysis, and the spectrums are recorded in our computer. And having done that, this is how the weighing process, sample analysis has been done in a laboratory at King Mongkut Institute of Technology, Landrapa. Yes, thank you.
This is the spectrum of the bamboo wood chip and the ground bamboo. We can see because of bamboo wood chip or biomass, ground biomass has the major constituent of pure lignin and pure cellulose. So we can see the peak of the pure lignin and pure cellulose here. lignin peak here and uh, peak of cellulose here, and also the peak of water in the bamboo sample. The peak of lignin and the peak of cellulose occur in the spectrum of biomass because the lignin structure contain the hydrogen bond, OH and CH bond, and cellulose has the OH bond when the uh, lignin has the CH and OH bond. So when the bond when the NIR radiation radiate on the bond, it absorb radiation, NIR radiation, and vibrate in the overtone and combination mode. So occur the peak when it absorbs the radiation. This is the different type of spectrum from different biomass we collect in Nepal. And you can see the structure of different biomass type is the same. Uh, where we can see the peak of lignin, peak of cellulose, and peak of water. But we have to notice that there is the parallel shift of the each spectrum of each biomass collected. Uh, even so, we cannot compare whether which kind of biomass have higher lignin or lower lignin, or higher cellulose or lower cellulose, or even water. We cannot differentiate. Even even it is the same moisture content, like because of the um, biomass we collected is dry before we scan, and when we scan it's still dry, so the moisture content should be same, but we can see the different peak, the different height of the peak indicate apparently as the water is different. This is the due to the different size of biomass when scanning. Like corn cob has big size, while the rice husk is small size. So with a different size of biomass particle, so make the parallel shift of the spectrum. So to remove the parallel shift of spectra, so we have to do mathematic manipulation using vector normalization. In this case, to remove to make the spectrum to have a common feature. So as you can see, at the peak of water, the spectrum come close together due to the moisture content of different type of biomass we scan has the similar uh, moisture content. So but you can see clearly there is a different height of peak in the lignin peak and the cellulose peak due to different type of biomass like rice husk, corn cobs, corn stover. There is a different constituent of the lignin and different constituent of cellulose. So we can see the height of the peak is different. So we can compare which one has a higher lignin, which one has higher cellulose. After we scan sample, so we have to measure for the reference properties. In our case, is the energy characteristic of the biomass sample. So we use three different type of instrument, which are bomb calorimeter for measure heating value, higher heating value, and elemental analyzer to measure the carbon content, hydrogen content, nitrogen content, sulfur content, and to calculate the oxygen content. And we use also the thermogravimetric analyzer to get the combustion performance and the pyrolysis performance, such as the uh, ignition temperature, ignition index, burnout index, combustion index, uh, temperature, peak temperature for the hemicellulose degradation, and peak temperature of the cellulose degradation, and so on. And then we have to continue to make a model related the spectra and reference parameter, which is energy parameter properties. After we get the result of the spectrum from biomass scanning and from the uh, energy properties of sample, so we have to make a model or make an equation by the mathematic algorithm to calculate the biomass energy properties. This work we do on bamboo, wood chip and ground bamboo, uh, and we publish our research result in the renewable energy with the Dr. Excel Funke from Karlsruhe Institute of Technology. By partial least square regression algorithm, we get the model to predict the moisture content, volatile matter, fixed carbon, ash content, gross calorific value or higher heating value, and net calorific value or lower heating value of bamboo wood chip. And then we also calculate the volatile matter, fixed carbon, and ash content, and gross calorific value and net calorific value of ground bamboo. Uh, you can see that we can make our model to calculate from spectrum of bamboo wood chip to check the moisture content. Uh, we obtain the R square or the coefficient of determination of 0.96, which is quite high accuracy, and then the bias is very less, is the minus 0.025, percent moisture content. And for volatile matter, fixed carbon and ash content, we get the R square of 0. More than zero point 0.8, from 0.81 to 0.86. And we can see that for gross calorific value or net calorific value, we can get the higher than 0.84 r square. Uh, but if we ground bamboo, the particle size is more homogeneous, so our gross calorific value and net calorific value has the higher accuracy. Our model has a higher accuracy in predict the gross calorific value and net calorific value, where the r square is more than 0.9, and the bias is very less. So uh, I would like to confirm this near infrared spectroscopy can work to detect the energy properties of biomass. So we now continue our work in our research center, uh, as Professor Beam have told you about our goal. I would like to introduce our research center. It is NIRS Research Center for Agricultural Product and Food in King Mongkut Institute of Technology, Lad Krabang, Thailand. You can contact me at pamanas.si@kmitl.ac.th. I would like to introduce the Nepal Technology Innovation Center, uh, where we have the collaboration on this NIR biomass sensor. Uh, so you can contact Professor Beam Prasad Shrestha at this email address, and you can visit our website by this URL that you can see, and to see our activity. So um, now is the end of our talk. Thanks for your attention.